Hello everyone, I am Dr. Sirajul Faizi. I welcome you in my YouTube channel. Today in this video I am going to talk about UV visible spectroscopy. I will cover in this talk introductions, principle and basic concept, some important terms, instrumentation, applications, conclusions and references. So let us start with the introductions. Spectroscopy is a technique that measures the interactions of molecules with electromagnetic radiations. Light is the near ultraviolet and visible range of electromagnetic spectrum, has an energy of about 150 to 400 kJ per mole. The energy of light is used to promote electrons from the ground state to an excited state. A spectrum is obtained when the absorption of light is measured as a function of its frequency or wavelength. The absorbance of solute depends linearly on its concentration, and therefore absorption spectroscopy is ideally suited for quantitative measurements. Spectroscopy measures are very sensitive and non-destructive and requires only a small amount of material for analysis. Application of derivative technique of spectrophotometry offer a powerful tool for quantitative analysis of multi-component mixture. Now, basic and principle: ultraviolet visible spectroscopy for 200 to 800 nanometer studies the change in electronic energy level within the molecules arising due to transfer of electrons from pi or non-bonding orbitals. It commonly provides the knowledge about pi electron system, conjugated unsaturations, aromatic compounds, and conjugated non-bonding electron system. And UV visible is divided into the ultraviolet and visible regions, since the absorptions of ultraviolet or visible radiations by molecule lead transitions among electronic energy levels of the molecules. It is also often called as electronic spectroscopy. So, nature of electronic transitions: the total energy of molecule is the sum of its electronic, its vibrational energy and its rotational energy. Energy absorbed in the UV regions produces changes in the electronic energy of the molecule. As the molecule absorbs energy, an electron is promoted from an occupied molecular orbital to an unoccupied molecular orbitals of greater potential energy. You can see here the relative energy of orbital most commonly involved in electronic spectroscopy of organic molecules. You can see the increasing order of their energies into pi star greater than less than into pi star, and pi star, sigma star, and sigma to pi star and sigma star is higher energy. So what is the principle of absorption spectrum? Beer's and Lambert's law. The greater the number of molecules that absorb light of a given wavelength, the greater the extent of light absorptions, and lighter and higher the peak intensity in absorption spectrum. This makes the basis of Beer's-Lambert's law, which states that the fraction of incident radiations absorbed is proportional to the number of absorbing molecules in its path. When the radiations passes through a solution, the amount of light absorbed or transmitted an exponential functions of molecular concentration of solute and also the functions of length of the path of the radiation through the sample. Therefore, log I naught by I is equal to epsilon Cl, where I naught intensity of incident light or light intensity passing through a reference cell. I is the intensity of light transmitted through the sample solutions. C concentration of sample in mole per liter, the path length of the sample in centimeter. Molar absorptivity or molar extinction coefficient epsilon is numerically equal to the absorbance of the solution of units. Molar concentration C is equal to 1 in a cell of unit cell, and its units are liter mole per inverse centimeter per inverse. The ratio I by I naught is known as transmittance T, and the logarithm of the inverse ratio I naught by I is known as the absorbance A. Therefore, log I by I naught is equal to minus log T, epsilon Cl, and log I naught by I is equal to A epsilon Cl. So friend, spectral measurement. The UV visible spectra are usually measured in very dilute solution, and most important criteria in the choice of solvent is that the solvent must be transparent within the wavelength range being examined. Some common solvent with their lower wavelength cutoff limit below these limits. The solvents show excessive absorbance and should not be used to determine UV spectrum of the sample. Acetonitrile 190, water 191, cyclohexane 195, methanol 203, and 95% ethanol 304. Of the solvent listed in table, water 95%, ethanol and hexane are the most commonly used solvent. For recording the spectrum, 1 cm square quartz cell is commonly used, and this requires approx 3 ml of solutions. Now friends, solvent effect. Highly pure nonpolar solvents such as saturated hydrocarbons do not interact with the solute molecule either in the ground or excited state, and the absorption spectrum of a compound in this solvent is similar to the one in pure gaseous state. However, polar solvents such as water, alcohol, etc. may stabilize or destabilize the molecular orbital of molecule either in the ground state or in the excited state, and the spectrum of compound in this solvent may significantly vary from ones recorded in a hydrocarbon solvent. Some important term: chromophore. The energy of radiations being absorbed during the excitation of electrons from a ground state to excited state primarily depends on the nuclei that hold the electrons together in bond. The group of atoms containing electrons responsible for the absorption is called chromophore. Most of the simple unconjugated chromophore give rise to higher energy transition of little use. So friends, you can see the oxochrome, bathochrome shift or red shift, hypsochromic shift or blue shift, hypochromic effect and hyperchromic effect. Now the instrumentation, you can see the flow chart. So radiation source: tungsten lamp, hydrogen discharge lamp, deuterium lamp, xenon discharge lamp, mercury arc. Monochromator: essential element, intense light, dispersing element, prism or grating exists detector: barrier layer cell, photocell and photomultiplier tube. What is the applications? Application to organic compound: detection of conjugation, detection of geometrical isomer, detection of functional group, qualitative analysis, detection of impurities, quantitative analysis and kinetics. I hope friends, this video will be helpful to you. If you like this video, then subscribe my channel, and thanks for watching.